Based on the central limit theorem, so it says the estimate sources cannot be Gaussian. Okay, so the next question is how to quantitatively measure independency. OK， 好，接下去有个问题，怎么去量它的独立性或是非高斯性 ？OK， 怎么去量？好 ，OK。So of course, the most easy way we can measure the non-Gaussianality by the kurtosis. Okay, kurtosis is something to do with the force moment, right? Okay, in statistics, for the random variable, what will be the mean? Mean is something to do with what? The first moment, right? 一阶动差就是平均值。What about the second moment? The variance, right? What will be the third moment? Skewness, right? Right. The long tail shift to the left or shift to the right, right? Now, the fourth moment is something to do with the kurtosis. It's about, you can find that the distribution will show the peak or is flat, okay? Now, here's the definition about the kurtosis. Okay, again, E is the expectation, 期望值, force moment, okay? The force power of Y minus blah, 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 okay? That's the kurtosis. Now, it says, because, as I mentioned, when we do the ICA, usually we will go for the centering and whitening first, right? So that after the pre-processing, the whitening of the variable Y, the variance got to be 1, is 1. So we can replace this with just -3. Okay, that's kurtosis. Now, it can be proof. It can be proof for a Gaussian distributed variable Y, its kurtosis is 0. It's 0, okay? It can be proof, okay? 好，那个是可以证明的，我们当然就跳过。高斯分布所对应的 kurtosis 是0。Now, so now for ICA, if we measure the independency or Gaussianality, the objective will becomes what? We try to maximize the kurtosis of your estimate value. Because the kurtosis could be positive or negative. We try to maximize. Why maximize? Because for Gaussian, the kurtosis is 0, but it could be negative. So usually we will take the square, okay? We take the square. And then you try to find the projection, okay? Trying to find the projection. W means the projection, okay? Try the projection direction. That will maximize your kurtosis. That's the easy way to go, okay? Kurtosis, because Gaussian will return the minimum, okay? The minimum absolute kurtosis value of 0, okay? 所以呢，我们可以找任何一个投影，可以让它投影完后的那个 component 的值呢远离0 ，OK？ 那因为 kurtosis 有正有负啊，所以我们取绝对值。或是取它的平方 ，okay? So that's the either you can take the square, okay, or we can take the absolute. Usually we go for square. Why is that? Because when you try to solve for the optimization problem, usually you need the gradient. You need to take the derivative, okay? 你要做微分，一般微分呢找平方微分是最容易的。好，这是为什么一般我们都习惯。We take the square, okay? Take the square, okay? Now it says something like, for this one, the kurtosis, okay, is a Laplacian distribution. It's corresponding. If we have the Laplacian, okay, distribution like this, it's corresponding. Kurtosis is 3, okay? It's 3. It's positive, but. And it is a so-called super Gaussian. It's so-called the super Gaussian. The category is so-called the super Gaussian. But if the value, okay, the kurtosis is negative, then we say is sub-Gaussian, okay? Like the uniform distribution is more flat. Distribution is flat. And you can see a peak here, okay? Just like the Laplacian. Most of our human voice, okay, our human voice belong to the sub-Gaussian. But when you shouting or laughing or coughing, then it will become super Gaussian. Okay, it can just for your information. It means what? Because we the objective try to maximize the kurtosis. So if you have three sources to estimate, what would happen if you go for the kurtosis? Because the objective try to maximize the I didn't say it here. For a sub-Gaussian, is bounded below. The value cannot be larger than 2. But for super Gaussian, the maximum value basically is unbounded. So when you solve for the estimate the independent component y1, y2, and then y3, what will the optimization goes? You will make everything to be super Gaussian because you will have the maximum gain. It means what? If the estimate sources could be, some might include super Gaussian, some might include sub-Gaussian, you have better not to use kurtosis because based on the objective here, it will make every estimated sources to be super Gaussian. 因为它获利最大嘛，为什么管它呢？对不对？不是吗？因为你是这样做，他就这样猜啊。那我们讲过啊，sub-Gaussian is bounded by 2, but for super Gaussian it can be unlimited. So you must be very careful. Okay, when you the other problem is because it's about the force power. So if the original value is 10. What will be the force power? So it could be affected by outliers. 就是你有一个异常值的话 ，noise， 它的影响会太大，因为你拿4次方嘛，本来只差10的，会一下子变了，可以不是吗？10的3次方1000嘛，10的4次方10000 ，right? The value has to be magnified from 10 to 10,000. That would be another point. I didn't say you should not use kurtosis, but must be very careful to use it. Okay, that's kurtosis. Okay, so that's it. Most of the case we don't use kurtosis, but it's one of the choices. The more practical way to measure the non-Gaussianarity or independency is based on net entropy. Okay? It's based on entropy. So to talk about the net entropy, we need to define entropy first. Some of you have heard this in my MV course last year, but I need to repeat it again because entropy is very important for machine learning and also for deep learning. Okay, 深度学习. Okay, the loss function in the deep learning, a lot of is based on entropy. It's based on entropy. So let me just repeat it. Okay, just refresh it. Even some of you have learned this before, but just try to refresh your memory. Okay, I will redefine entropy. Then net entropy is positive. But anyway, this is a more popular way to measure the non-Gaussianarity. Okay, cool. So before that, let's talk about entropy first. Okay. Now, to talk about that, it's based on the information theory 资讯理论资讯理论这个是他们资讯工程几乎一定要上的课 OK， 不，我很快讲一下，没有太多时间。Anyway, suppose we observe a signal, okay, in a time interval from time 0 up to time t. Or you can think of you throw or roll a die for t times. Okay, up to you how to interpret. Okay, so t could be the observation period of the time, or the number of trials. Okay, when you roll a die or a coin. Okay, that'd be fine. Okay, either way, that'd be fine. Now, and every tau, every fixed period tau here, we observe the possible outcome. You measure the possible outcome. We call it V. Okay, then V sub I means the V1 means the first period of the second period, or the first trial, second trial, and so on. And suppose the value could be, we have a total of, for this case here, suppose we have a possible outcome. For example, if you roll a die, the possible outcome will be what? 1, 2, 3, 4, 5, and 6. Okay, 6. It has to. So for the very first time, you might have a possible combination, right? Possible outcomes, impossible outcome, 1, 2, 3, 4, 5, or 6. Then what about the second? The second trial, we still have, right, impossible outcome. So in a long run, after t trials or after t observation, and each observation, the time interval is tau. So there's a total number of observations. And each time you have impossible outcomes, right? So we put them all together, then this will be the possible outcome combination. Everyone follow me? 因为每一次有 n 个可能性嘛，那你一共丢了几次？丢了 t over tau 次。Okay? This is the possible combination that you can observe. Okay, the output. Everyone follow me? Okay? So just like you roll a die, the first will be 6. Then the second, you will have 6 possible outcomes, right? Just like if you toss a coin, the possible outcome will be 2, right? Head or tail, then and so on and so forth. Okay, so this is a quantitative measure of the complexity of information. That's something we are talking about, the information theory, how to measure the complexity or uncertainty 因为在资讯里面，它是在谈这个资讯本身的复杂度有多高，或是呢这个事件的不确定性有多高。Okay? So basically, because it takes the power for the number of trials, okay, or the total number of observations. So this value could be too large, right? Too large could be too large. So the easy way is to take log. We take log. Okay, it won't change. Okay, the significance of the possible combination or the uncertainty or complexity. But when we take log, the power, okay, can be something like this, right? This is much easier to handle compared with this value because you will see a lot of 0, right? A lot of 0. Yeah. Then that's it. Almost the end about information theory. That's the measure, to measure the complexity or uncertainty of information, but we are not done yet. Okay, now, if the probability of each outcome is equal, just like we roll a die, each possible outcome is 1/6, okay? It's 1/6. Then n can be written down like this, right? Everyone follow me? The probability, okay? Like this, right? We have n outcome. Then n is the inverse of p, right? P is the probability, right? So this can be, we can write down this as 1. P is the probability, okay? We'll put a minus here. Why is that? That's because we have minus 1 here, okay? Everyone follow me? So, okay? It is very important to know that, okay? Now, if the outcome is the probability for the outcome, they are not equal, so then we have to release it, okay? Now, we suppose we make n trials, okay? In a long trial, n means we for example, you roll the dice for 100 times, then n equal to 100. 就是你丢骰子丢了100次，这个 n 呢就等于100 right? Then what will be the probability that the outcome is 1, 2, or 3? That will be the, okay, I here is the number of the outcome value in a long trial n. Everyone follow me? That's the estimate, okay? I put a hat here, means the estimate, not from the true population. Okay, for some outcome I can be written down as I put a R. R is the number of observation or the frequency for some outcome VI in a long trial. Okay, right? So this we can write down this as a what? We can write it down just like this, okay? We can write it down like Ri, because we have a number of outcome with the value of Vi, okay? Times log Pi, okay? Here, okay, that's what we are doing. Okay, I need to put, because the summation of Ri should be equal to T over tau, right? Right, the summation, right? The total sum, this is the total number of trials, right? Then this is the number of trials, okay, that you will get the output Vi, then put a summation, it will be something like this, okay? Okay, that's what we got here, okay? Then we need to do this for OI. Now, for this equation here, if I times n here, okay? If I times n here, n is the number of trials, then I divide it by n, right? We can cross out this 2, okay? It doesn't matter. And what is this value? What is this value? This value is right here. See that? It's right here. So this can be, we can write it down as that's the finally what you got here. Okay, that's what you got here. See that? Okay, that's what you got here. Because n could be, we can just drop n here. It's a constant because the number of trials doesn't matter. Okay, we just drop it. So that's how we define the entropy. Okay, so that this is how we define entropy. Okay, so the entropy is defined by Pi times log Pi for all possible outcome I. Okay, that's the final form for entropy. Entropy is used to measure the uncertainty or complexity of an event. 这个事件它发生的复杂度有多高，或是不确定性有多少。OK， 它是一个好的 measure 不像原来的，因为原来这个值太大。OK， 看到一堆零这个是。So first, entropy, listen up. Entropy is nothing to do with the magnitude of the outcome value. 跟它的你观察到的值的大小一点关系都没有。Okay? You know what I'm saying? 跟它的值没有关系。Entropy is only something to do with the probability of the event. Nothing to do, I mean, even the value could be 10 or 0.1 or 10,000 or 1 million is nothing to do with its magnitude. 跟它的值的量的大小无关，只跟几率有关，只跟事件的几率有关。Now, let me ask you, log 1 equal to what? Everyone know what I'm saying, right? Log 1 is 0. It means that if log 1 equal to 0, because p is the probability, it means what? You have some value, some event have the value of 1. It means what? There is no information content at all, because there's only one event, and the only one event. There's no other probability, there's no other possible that you can observe anything value after event I. So the uncertainty is 0. 不确定性是零。Okay? That's something it tells you that. Okay? So we use a lot even for the ecology or economy. It can to measure how complexity of the species in an island, for example, or it can measure the activity of economic market. Okay, if the entropy equals to 0, it had better to do something else, right? 在整个岛，你去调查物种，发现呢，它的 entropy 等于0，那表示说，这个岛上只有一种生物。经济行为一看，它的 entropy 等于0，那不是完蛋了？只有一种经济行为，其他没有。Okay. So anyway, entropy is a measure of complexity. Then next, you might ask me one question. When I say log, what could be the base? Based on what you have learned since high school, it can be, usually you might take 2, right? Or 10, right? Or 1. Now, most of the case, we take E, then we use, okay. But for the computer science guy, they prefer 2. Why is 2? Why 2? 那个先掉了，为什么2？ Because the bits, there's only a bit, it's only 0 or 1. So you know, for computer science guy, what does it mean by entropy? Do you know that? If the value equal to 5, it means what? I mean, the value is not between 0 and 1. Even we're talking about the probability, but the output, no, it does not have to be 0 or 1, or anything between 0 and 1. Okay, it could be 5. So for computer science guy, when you have the entropy equal to 5, it means what? You need 5 bits on average to represent the event or to code something. You need to take 5 bits, okay? So for the computer science engineer, they would like the entropy should be as small as possible. Because it's very small, it means what? For this case 5, it need only take 5 bits to transfer the information from location A to location B. Or it need only 5 bits to store the information, okay, in your storage. So the value you will expect should be as small as possible. Anyway, but most of the case we take E, okay, the natural log, okay, as the basis. But it's fine, even you want to take 10, unless you're doing something with the computer engineering. Otherwise, most of the case we don't take 2, okay. But anyway, log of 1 equal to 0. You must keep that in mind. Okay, means there's no uncertainty. There's no information at all. Okay, no information at all. Okay, that's the entropy. Let me summarize. Re-emphasize again. Entropy is nothing to do with the magnitude of the event value. 跟事件的值的大小一点关系没有 ，it only something to do with the probability. OK， 就跟几率有关。可是记得哈，它的 outcome 的值不是介于0跟1哦。虽然我们谈的几率一定是介于0跟1之间，可是它的 entropy 呢，不是哦，不是哦，看不是哦。Why we put mass here? You know, because p is a probability. What about log 0.1? Because log t is negative, it's negative. 因为它只介0跟1之间，它的值一定是负的。0跟1嘛，不是10的负1次方，我提出来负等正啊。So anyway, the value best is not negative. Okay, it's not negative. Anyway, okay. I need to go fast. Okay. Anyway, this gives you the example. If the event is only A, we only have one event. Then the probability must be equal to 1, right? Then the number of bits required is 0. Okay? If you have 2 events, each one with the probability of 1/2, 0.5 and 0.5, and when you calculate the entropy will be 1, which means you need only one single bit to represent the possible event for A or B, and so on. I will skip the next. The next one is a very classical example. There's the host rate with 8 hosts from A, B, C, D, E up to H, but with different probability. Now, you want to send the message, okay, for someone to tell him or her which horse win the game. Suppose A always win the game, win the race with the probability of 1/2 and blah blah blah. So because you have 8 horses, usually you need how many bits to represent each individual horse? 8. It got to be 3 bits, right? 3 bits, right? Well, why is 3 bits? Because 3's power of 2 is 8, right? 不是吗？一定要3个 bit 嘛，才能够代表嘛。But if you consider all this probability, because 1/2, A will win the game, which means most of the time you only have to transfer 1 single bit. Why is that? Because A will win the race, okay? So most of the time, you just send out 1 single bit, not 3 bits. Otherwise, usually you might just put 000, for example, to represent A, right? And 001 could be represent B, and so on and so forth. But if you consider all the probability, I will skip the details, okay? The average is only 2 bits, not 3 bits. It's 2 bits. But sometimes you need to transfer more than 3 bits, but that's another story. Okay, if you are interested, just take a look. Okay, because it's so-called the prefix. Okay, prefix, which means, see that? If you transfer 1 bit, just put 0. And then for 2 bit, it should start from 1, not 0. Anyway, I'll skip it. Okay, but you know, everything is something to do with the probability. Okay, not the magnitude. Okay, not the magnitude. So don't forget that. Now here, with the knowledge about the entropy, now I can talk about the Carroll divergence, cross entropy, and which use a lot in deep learning. Okay, or to measure the similarity. Okay, now we know this is how we define the entropy, right? Now, let's further talk about the Carroll divergence because it's very important in deep learning. In deep learning, it's a very important measure for the loss function. Okay, here's how we measure. Okay, actually, Carroll divergence is also known as relative entropy. Okay, there's a relative entropy. Okay, now here's the definition of the relative entropy. No minus sign here, no minus sign here, 没有复数. No, actually it can be proved. This value is non-negative. Okay, the minimum value is 0. Now it tried to, Carroll divergence is trying to evaluate the similarity between the distribution P and distribution Q. Okay, know what I'm saying? Okay. 它是在两个 distribution 之间的差异 Okay, so one could be the ground truth. Okay, the other one could be the estimate probability. Now you do all your effort to make P equal to Q. Okay, then times P here is the mean, right? It's nothing but the mean difference between P and Q. That's it. Okay, the so-called Carroll divergence is very important to measure the difference of two distributions. Okay, that's it. And the value cannot be negative. It must be. And again, now they are different. When you calculate the Euclidean distance, when you drive, for example, from Taipei to Kaohsiung, will be the same when you do the driving from Kaohsiung to Taipei, right? Make no difference. The distance or the required driving time is the same. That's a Euclidean distance, but for cross entropy, for the Carroll divergence or relative entropy, they are not equal. They are not the same. Okay? Well, in our field, it's called a non-metric distance. Non-metric distance. A metric distance must be satisfied what? From A to B must be equal to B to A. From A to A must be equal to 0. For a triangle, the summation of two edges must be larger than the third edges, right? 两边会一定大于第三边嘛 But for the non-metric distance, no, you won't hold the requirement here. Okay, it's different. But anyway, that's another story. Okay, it's a Carroll divergence. Anyway, now again, let me say something about the computer science guy. Do you know what is the value represent? it says, I want to use Q to represent the coding of P. Then how many more bits I require? 也就是说，我原来的我描述一个事件，我需要用，比如10个 bit， 然后我现在用另外一个 event distribution 来表达这10个 bit。那比如说 if the output is true, for example 2, it means what? You need 2 more additional bits by using some coding of Q to represent the original distribution. 听懂我在说什么？本来原来要用5个，可是你现在用另外一个 coding 的技术去描述。But anyway, if P equal to Q, which means what? You don't need any additional bit, okay, right? 你都一样嘛，就不用。可是呢，不一样的话呢，表示说你为了描述这个事情，原来只要5个 bit， 那你出来它变成2个 bit， 表示说呢，你可能要用到7个 bit。你要多2个 bit， OK， 那是他们计算器喜欢用的。But anyway, that's cross entropy. Okay, this chaos divergence is well. Actually, if you want, you can think of this as what? Right? Again, it's nothing but the distance. 它又是距离的2侧，没有看到吗 ？The difference between log P and log Q is another distance, but based on the entropy. Okay, then we take P as the weight. That's it. Okay, that's it. Right. I'm sorry. Okay, but anyway, we can separate it into 2 terms. Right. So if this term is a constant, is the ground truth, for example, it's ground truth, no matter what you estimate the distribution. So we can drop this term. We might drop this term, and that is so-called. 就是说我们把这个因为这是ground truth嘛，不管你怎么弄统针都一样，不管你怎么裁它也不会变。So we might drop this term. And that's so-called cross entropy. Okay? Don't forget to put the minus sign here. Okay, we have a minus sign here. 这个叫做 cross entropy. 所以 cross entropy 基本上也是从 relative or chaos divergence 来的了。就是一样，因为它前面是常数嘛，常数就不用管了，我们只留下后面这一项。那我们就看这个ground truth跟我们猜的那个 distribution 它们之间的差异。好 ，OK？So that's something you need to keep in mind because when we talk about the delearning, we need to go back to talk about these measures again. Okay, that's so-called cross entropy. Okay, I skip this part for the time being because I need. Okay, if I have time, I will come back because I need to talk. Okay, with all this information here, now we can talk about how to measure the non-Gaussianarity by net entropy. Okay. Again, it can be proved. A Gaussian variable will have the largest entropy. It can be proved mathematically. Okay. But if all the random variables have the same variance under the condition, but we can always set up this restriction, right? By what? By whitening, right? 我前面不是讲 centering whitening 吗？做完 whitening 以后呢，所有的 variance 都一嘛 right? So when you try to compare all the different distribution, no matter it's a Gaussian or uniform or gamma distribution, blah blah blah. Okay, everything. First, when you do the whitening, then all the variance will be unique. Okay, they will have the same variance. Then it can be proved a Gaussian variable will have the largest entropy. And now you know how to set up the objective, right? So we say because the separate signal cannot be Gaussian. And Gaussian will have the maximum. So that we try to minimize. Right? Okay, that's the idea. Okay, that's the idea. Okay? So the net entropy is defined by if Y Gaussian, H means the entropy. Okay, H means the entropy. Y is the variable. It's a Gaussian random variable. It's both a lowercase means it can be a vector. Okay, it can be a multivariable. Okay, multivariate. Okay, variable. Okay, it's a vector. So as we know, because if Y is Gaussian distributed, its corresponding entropy will be maximum, right? Will be maximum, and Y is the value. I mean the sources you want to estimate. You know this value cannot be negative, right? Because as I just mentioned here, okay, under the same variance, a Gaussian variable will have the largest entropy. It can be proved. So this is how we measure the net entropy. Because why call net entropy? Because usually net entropy we need to put a minus sign. But this net entropy, as you see here, it cannot be negative. Okay, because we subtract the entropy of Y from the Gaussian distributed random variable. Okay, so as I say here, Y is a Gaussian random variable. Okay, it can be a vector, a multivariate. Okay, so that's how we measure. Okay, so we would like this value to be what? If this value is getting closer to 0, it means Y is still Gaussian. Everyone follow me? 也就是说，你算出来以后，这个 Y 呢，它这个值呢，算出来这个 J 的值等于0，表示说这个 Y 呢，这等同高斯嘛，不是吗 ？Everyone follow me？ 因为高斯是最大嘛，你有减掉，那你发现这两个一减等于0，要表示 Y 根本没拆开嘛，不是吗？因为它还是高斯嘛。So we like to maximize the difference. We try to maximize the net entropy. Everyone follow me? What I'm saying? Okay, that's what we are doing here. Okay. Well, actually, it can be proved. Okay, you can find the proof from any information theory textbook. Okay, actually, this is the value is a constant. Okay, suppose this covariance. Okay, the determine it got to be an identity matrix after the whitening. Okay, and this value is a constant, a Gaussian. So this value is a constant. So actually, it can drop this. Then we try to maximize. We just need to focus on the entropy here. That's it. Okay. Now, here's a question. Well, to calculate the entropy, you need to know the probability, right? We know nothing about the probability. So all the remaining work is engineering. It's something to do with engineering work. And some guy come up with a very smart way, and it works. Anyway, let's just keep that. Let me keep. So this is a general term. You can E means expectation. Okay, expectation. V is a Gaussian. Okay, is a Gaussian variable. As I say, you can drop this term. Actually, you can drop this term. You can drop this term. All you need to do is try to maximize GI. Okay, it means that you can use a lot of different G1, G2, G3, blah blah blah. Okay. As I mentioned, there's no way you will know because it's a blind source separation. When I say blind, means I don't know nothing. I know nothing about the probability. But some guy, it just use a non-quadratic function to replace the probability, and it worked. I believe when this guy tried to develop this algorithm, it must be trial could be more than 10 or 100 different functions. And finally, he suggests three, okay, three. Why it cannot be Gaussian? Because when the original author developed the optimization algorithm, it will involve first derivative and second derivative. OK， 因为他那个最佳化的问题哦，今天没有时间，我可能也不会讲细节。This is the first derivative, the second derivative. It will need up to second derivative. So that's the only reason why it cannot be it cannot be quadratic. What does it mean by quadratic? You use x2. What is the first derivative? It will be 2x, and then what up to the second derivative? It will be a constant. Then you will get stuck because it doesn't know where to go. 知道我说什么？Because the optimization basically you want to estimate it's a gradient descent. Okay, gradient descent. This is the learning rate. This is the direction. Okay, this is the direction. I mean, in the IC is a little bit more complicated, but anyway, that's the basic idea. Okay, this is the current parameter value. This is for the next iteration. Then L is your loss function. For example, your objective. Okay, we take the derivative with the current value. Okay, and this is the step size. Okay, and this determines the direction to go. Okay, you will determine the direction to go. So if you take the quadratic function, then you will get stuck too, right? No matter what you change, this value will be fixed. Then you will get stuck. 你会被限制住嘛？就像爬山，你爬山你 right? You starting from here. If this will be the top of the mountain, you need to decide, right, what direction to go, and what should be the stride to move, right? That will determine your the step size. Okay, that would be basically the procedure for optimization. But for ICA, there's a very famous algorithm called fast ICA. Eventually, we can drop. We don't need this step size at all. So it's very fast. But anyway, it cannot be quadratic because if you go for quadratic, you will get stuck. Okay, you will get stuck. That's the only reason. No other any reason for that is non-quadratic because it will take up to the second derivative for that. Okay, that's it. That's the only. So anyway, we can drop this term and we just use single one so that it's just trying to maximize. Okay, it's just trying to maximize. That's it. Okay, that's it. And you need to find the projection. You need to find the projection so that the corresponding gradient. Okay, I'm sorry. The non-quadratic function is maximized because, as I mentioned, because this is a constant, and we take just only one single g. Okay, just one single non-quadratic function. Actually, you can take 2 or 3 or more. But later on, when Carlos come here, he will just show you how to run it. I will finish this. Okay. The fast assay suggests 3 different non-quadratic functions. Of course, you can think of one of it got to be kurtosis. It must be kurtosis. Okay, just say a word. Okay, I will finish that. Then you can stop on your assignment.